Okay, so 6.9 is integrating using U substitution. So when you hear U substitution, okay, I want you to think of it as the opposite of the chain rule. Okay, so the chain rule, we used it when we were doing the derivative. U substitution, we're going to use it when taking the antiderivative. So this right here is U substitution. Okay. And all you need to know again is it's the opposite of the chain rule. Okay, so before we look at U substitution, off to the side, we're going to write some rules for it. So rule 1, this rule is called the inside function rule. Pretty much that it tells you if we have a function that has some part of an inside function like a parentheses or a square root, then we are going to choose that inside function as our U. So choose U as the function inside. So for example, let's say we had x plus 4 squared. The U would be x plus 4. It's inside. Okay. Or if we had the square root of x minus 2, the U would be x minus 2. It's inside. Okay. Well, rule 2 tells us that, well, sometimes we don't have an inside function. So we're rule 2, which is called the derivative presence rule. Okay. This tells us that if we can't choose an inside function, let's try to choose a U value that when we take the derivative, that derivative is going to cancel with something already inside of the integral. So ideally, the derivative of U should appear in the integral. Okay, and we'll see more of that example in the problems. Okay. And then the last thing we're going to write in the margins is what it means to do U substitution. So this is, again, back in Algebra 1, Algebra 2, when you were learning how to factor a quadratic. So when you first learned about U substitution, you were given higher order equations such as x to the 4th plus 4x squared plus 4. Okay, and then you were asked to factor this. Okay, well, when you were in Algebra 1, Algebra 2, you would look at this and say, well, I can't take out a GCF. So then from there you kind of get stuck. Okay, what should I do in order to factor this? Well, this is where U substitution came into play, because you could say let U equal x squared, okay, which implies that U squared is equal to x squared squared, which is x to the 4th. So that means instead of writing this in terms of x, we were able to write it in terms of U. So this is now U squared plus 4U plus 4, which is now a quadratic that we all know how to factor. Okay, and this is U plus 2, U plus 2. Once you're able to factor this, you plug back in your U, which is x squared, and we get our answer of x squared plus 2 times x squared plus 2. Okay, this is Algebra 2. So hopefully it looks a little familiar. because this is the same concept we're going to do for calculus. Okay, and the idea behind this is by using U substitution, we are going to make our integral easier to solve. Any questions about the rules or the Algebra 2 example? Okay, so looking at number 1, we have the integral of 3x minus 4 to the 5th power dx. Okay, so we could use the first rule, which is the inside function rule, and let u equal what? 3x minus 4. Okay, so we're letting u equal that inside function. Okay. Once we have u, then we know that du dx, or the derivative of u, is going to be equal to 3. Okay. And our goal here is to have this integral all in terms of u. Okay, which means that we can no longer have dx at the end, but instead we need du. Okay, so in order to get dx by itself, so we can substitute it back in, we would multiply both sides by dx, okay, then we would divide by 3. So we have dx is equal to du over 3. Just isolating a different variable there. Okay. Then I plug everything back in. So I have the integral of u to the 5th du over 3. Okay, so I'm substituting my u in, and then I'm also substituting my dx. So now everything is in terms of u. Okay, I can simplify this by using that constant property, and I can take out a 1/3. So now I have 1/3 integral u to the 5th du. Okay. It is much easier to find the antiderivative of u to the 5th versus the antiderivative of 3x minus 4 to the 5th. Okay, so what would be the antiderivative?
u to the 6th power divided by 5?
Close, divided by the 6, yes. So 1/3 u to the 6th divided by 6 plus c, right? Because in the original function, we don't know if there was a constant that when we took the derivative, it went away. So we always do that plus c. The du is gone. We took the antiderivative. Okay. Well, I can rewrite this as 1/18 u to the 6th plus c. I just took out the 1/6 from the u to the 6th and multiplied it by 1/3, and I get 1/18. My last step here is to plug what we set u equal to back in. So now I put everything back in terms of x. So this is 1/18 3x minus 4 to the 6th power plus c. Okay, that is my answer. Not too bad, right? Think of this question as an A-B question. Right? This is just our stepstone to the BC ones.
That was a lot. Aren't you guys supposed to put it in the box?
Yes, I forgot to mention that. You probably should get a separate piece of paper. Because this is my notes right here, right? I always write it in the notes to make sure it fits, and I had to like draw arrows everywhere in the margins. But, or write super, super small. Or get a separate piece of paper and tape it into your notes. Yeah, we're going to end up skipping a question on, well, look, this is 10. I didn't even have room on 10. I had to use the paper next to it, and then I had to use all this space right here that technically you guys do your practice on. Yeah, so we're definitely needing a piece of paper for 6.10. Sorry, I should have said that in the beginning.
Merry Christmas.
Okay, so again, what we just did, that process was our baby stepping stone. Right? Hopefully, this wasn't too bad. Okay. No, the next one's another baby stepping stone. Okay. Okay. Compared to later? This is algebra 1 then. Easy.
Wait, what?
Compared to like, you mean like compared to like later units? Or 6.10?
What about like
Later units.
Later units, then this is algebra 1. Compared to 6.10, that's kind of hard because okay, let me say, every single problem except the last problem on 6.10 notes, piece of cake. The last problem is 6.10. I spent my whole conference working on it.
what?
Could not do it. Could not do it, so we're not doing it.
Oh, okay.
No, like I can do it, but I can't explain it. I was trying to explain it to Miss Wong, and then Miss Wong was trying to explain it to me, and it's too much. It's too much. It gave me a headache. I was done. I went home. I was done. That's what you get to look forward to, right? Okay. It's just because it had a lot of the inverse trig in it.
You just show it to us like
Record your faces.
6.10?
6.10.
Which question?
The last question of the notes.
And then like look up like every now and then like
No, I'm recording now. I record
Oh, no. Well, like, this is what's it?
6.10 when we do it in class. We're doing it together.
circle something that's important.
No, like, you do a separate video, like, just for the last question.
Just for the last questions? Oh, I can. Yeah, I can do that.
Only if explain it to us, but like in a passive aggressive voice. You get it, and then like no question, like professor. Yeah.
No, so what I do is I go through all of this, and I imagine you guys are there asking me every single possible question, and I'm making sure I know how to answer it before I teach.
That's a good way. That's like what you should. That's so nice.
Yes, so doing that problem, I was thinking of possible questions, and I could not answer those questions. So,
What if we just didn't ask questions?
anywho, we need to go back to this, right? Right? I'm recording, so you can listen to this whole conversation later. Remember, you guys are my audience, 7th period, because I get all the mistakes out in 1st, and you guys get the better notes in 7th. Okay. Okay, so now looking at number 2, what would you say our U value is? Good, because that is inside. So let U equal x cubed plus 4, which means du dx equals 3x squared. So notice this, not only did we use rule 1, where it's an inside function, we're also using rule 2. Because when we took the derivative, 3x squared, that is going to end up canceling out with 6x squared when we plug it back in. So we did rule 1 and rule 2 here. Okay, you'll see in just a moment. So first I need to isolate dx. And when I do that, I get dx is equal to du over 3x squared. So if I plug everything back into my integral, I have 6x squared u to the 5th du over 3x squared. Okay, so again, that's me plugging in u, and that is me plugging in dx. Okay, notice when plugging in the dx, is everything in terms of u? No. So with that second rule saying that we hope that our u value, when you take the derivative, will cancel something out, we see that it does here. It cancels out the x squared. Okay. And it also reduces the number. What's 6 divided by 3? 2. And then based off the constant rule, I can take the 2 out. So this is 2 integral of u to the 5th du. Okay. Now is everything in terms of u? Yes, so then we can take the antiderivative. And we know from the last one, the antiderivative of u to the 5th is what? U to the 6 over 6, and I bring the 2 with it, plus c. And I can simplify this by taking that 1/6 out of u to the 6. And so I have 2 times 1/6, which is 1/3 u to the 6 plus c. And then I plug in what u is. You know what I'm saying. 1/3 times x cubed plus 4 to the 6th power plus c. That is my answer. Okay, again, another baby stepping stone. This is AB. Okay, this is AB. Okay, so difference between AB, BC. AB stops here. They don't do anything more complicated. Okay, BC. Do you see in the notes where it says some tricky examples? You guys see that? Right before 6, 7? Some tricky examples. That's BC. Okay, any questions on 2? Okay, this is our last AB stepping stone. Okay, so looking at this integral, what would you choose to let u equal?
X minus 1.
Yes, square root of x minus 1. So let u equal the square root of x minus 1. Okay. Which we can rewrite the square root of x to be what? Oops. X to the 1/2 minus 1. Okay, so if I was to take the derivative, I would get what?
1/2 of x to the negative 1/2 power.
Good. And then derivative of negative 1 goes away. Okay, I can write this even nicer by saying du dx is equal to 1/2 square roots of x. Yes? Right, I just brought the radical back. Okay, the reason for that is I now have a fraction equal to another fraction, so I can get rid of the fractions by cross multiplying. See, algebra 2. Well, algebra 1. Okay, so then this means that 2 square roots of x du is equal to dx, because dx times 1 is dx. So now I have dx isolated, I have u isolated, I'm going to plug everything back in. So I have the integral of u squared over the square root of x, and then I'm plugging in dx, that is 2 square roots of x du. Do you see how our derivative of u gave us a function of x that can cancel? What can cancel? Square root of x, right? Which we want that to happen because we want everything to be in terms of u. So rewriting this is 2 integral of u squared du. I just put the 2 on the outside. Okay, now I can take the antiderivative. And what would the antiderivative of u squared be? Plus c, which I can take out that coefficient of 1/3 and multiply it by 2, and I get 2/3 u cubed plus c. And then last step, plug in u. So I have 2/3 times the square root of x minus 1 cubed plus c. Right? It's not bad. These are our A-B stepping stones.
And then would we have to do that and they give us an equation that we have to solve for C eventually?
Yes, we will. It won't happen in these notes, but what will happen is, remember in the other notes where we had to solve for C, where they gave us a point and we would plug in the numbers to find C?
Yes.
That's it.
Okay, thank God.
For now. Okay. Now let's look at number 4. Okay. Number 4, we now have trig functions. Okay. Not too bad. These are still our A-B stepping stones, right? I would say this is a little bit harder just because it's a trig function, but not super hard. Okay. So for this one, do we have an inside function? Technically, yes, right? That could be what? Cosine x. Okay, so let u equal cosine x. So du dx is equal to negative sine x. Which means dx is equal to du over negative sine x. Okay, this is good, right? Because what's going to end up canceling? The sine x. Okay. So then I do the integral of sine x e to the u du negative sine x. Sine x cancels. And then what should I do with that negative? Bring it to the outside. So I have negative integral e to the u du. Is everything in terms of u? Which means we can do what? Antiderivative. And what's the antiderivative of e to the u? E to the u. So this is equal to negative e to the u plus c. Okay, which means this is negative e to the cosine x plus c. That is our answer. If only, right? Okay. Here's our last baby stepping stone. Okay, I shouldn't say baby. A-B, stepping stone. Sorry. A-B. And my apologies for A-B because they're going to be watching this video too. I'm not saying that. I'm just saying harder. No, they will because they will do this. They'll do sections of this. No, I'm not.
She's saying you're the AB babies.
Yes, exactly, right? But then you guys are BC babies, right?
No, we're BC toddlers. There's a difference.
Okay, fine, toddlers. I'll give you that. I'll give you that. Okay, 5. Okay, so sometimes when we do use substitution, it's not enough. Okay, which means we might have to do use substitution again. That may also not be enough. So we could do use substitution a 3rd time. Okay, we could do it a 4th time, a 5th time, kind of like what rule that we did in the beginning. Well, what is it called? What's the guy's name? Yeah, Lahopitals, Lahupitals, Lopitals, whatever his name is. Yeah. Like that, where we would keep doing it until we got a answer for our limits. Okay. So, let u equal what? What could be our u value? 3x, because it's an inside function. Which means du dx is equal to 3. So dx is equal to du over 3. Have you guys saw the pattern yet? Like every time we solve for dx, du is on top? Yeah. That's why math is cool. You see the patterns, right? Okay, so then we plug everything in. We have the integral of cotangent u du over 3. I can take out that 1/3, move it to the front, and I have 1/3 integral of cotangent u du. Okay, now think back to all your trig functions for your integrals and your derivatives. Did we ever talk about cotangent?
Yes.
Oh, we did? Are you sure?
It wasn't individual.
Not individual, right? It wasn't by itself. Okay, so this means that even though we did the use substitution to help it simplify a little bit, this is not enough. Okay, so we have to think about the properties of trig. What's another way to write cotangent? Okay, 1 over tangent. What's another way?
Cosine over sine.
Cosine over sine. Cosine over sine. So we can say this is 1/3 integral cosine of u over sine of u du. Okay, that still doesn't help us solve it. However, what could help us is doing u substitution again.
What do we call this one?
We're going to call it w substitution.
Oh, okay.
And if you have to do it again, you call it v substitution. You just go through the alphabet. Okay?
I don't know the alphabet.
Okay, so for this one, do we have an inside function? We do? Technically u, right? But does that help us by saying w is equal to u? No. So that means we use rule 2. Rule 2 says whatever your u is, if we can take the derivative, will it cancel something else out? Sine, right? So we're going to let w equal sine u, which means dw du is equal to, what's the derivative of sine? Cosine. Cosine of u. Okay? That means du, if we isolate du, is equal to dw over cosine u. Remember, the goal is to cancel it out. Okay, so now I plug everything back in. I have 1/3 integral of cosine u over w of dw over cosine u. Can anything cancel? Cosine. Okay, which means I now have 1/3 integral of 1 over w dw. Is everything in terms of w? Yes, which means I can now take the antiderivative, which is what?
1.
Well, it's technically w is the limit of 1. I treat it like 1 over x. So then it would be.
Yes, treat it like 1 over x, and we learned what that one was. What's the antiderivative of 1 over x? Natural log, absolute value of w. So we have 1/3 natural log absolute value of w plus c. Okay. From here, we now plug in w. And what was w? Sine u. So 1/3 natural log sine u. Guys, it's not that bad. Plus c. I know you're probably running out of room. Okay, and now we have to plug in u. And what was u? 3x. So 1/3 natural log of sine of 3x plus c. That is our answer. It's so much fun. Okay. This is not even the hard ones, guys.
So, as I said,
It's too late to drop the class. You gotta stick with it. Okay, but don't you feel like really, really smart solving it? Oh. Like if you solve, okay, and look, the steps are not that's not that many steps.
I guess.
It's better than squeeze through a little bit.
Don't say that.
It's like making
so
mac
wrong.
and cheese.
No, don't mention squeezing.
Like baking cookies on the back of a dough box.
I think you eliminate.
Okay. For the most part, can you guys follow the logic? Okay, it's just tedious, right? It's not hard. Tedious, not hard. Okay. You don't need to take a picture, but I'm recording it. Oh my gosh. I mean, technically, should you have your phone out? Referral. No, I wouldn't. That's too much paperwork. Okay.
But you'll do this. Oh.
This is fun. This is fun. Hey, your teacher should like what they're teaching, right? Should like what they're teaching.
Well, I'm scared my teacher likes something like this.
Okay, so now it says tricky examples. The first tricky example, it says, when we use u substitution, we'll have to solve for x. Okay? What that means is when we use the u substitution, we're going to find out that we're not going to cancel out an x. So we're going to have to go back to the u substitution, individually solve for x, and plug it in. So, looking at this example, I've been waiting all year for integrals, guys. This is my favorite part of calculus. Yes. Waiting all year. Okay. Let u equal what? X plus 1. Why x plus 1? It's inside the radical. So that means du dx is equal to 1, because the derivative of x is 1. Okay, and that means dx is equal to du. Good, which is just du. Okay, if your neighbor's asleep, wake him up. Okay, so we plug everything in. We have the integral of x divided by the square root of u du. Okay, so notice this. Is everything in terms of u? No. Did we have anything where the derivative was able to cancel out an x? No. So what we need to do is we need to go back here to where u is equal to x plus 1, and we need to solve for x. Okay, so if we solve for x, that would be what?
X equals
U plus
1 minus u.
U minus 1, right? We just subtract 1 to the other side. We have x is equal to u minus 1. So I'm going to plug that in. The integral of u minus 1 over the square root of u du. Okay. So it doesn't look bad. The reason why they say it's tricky is you might forget and you'll just stare at your paper for 10 minutes wondering how to get rid of x. Okay? So from here, okay, how would we solve?
That's a really good question.
Okay, you've already learned how to do this by a method already. Okay?
We do it again. We take W.
No, you wouldn't do that.
What he said.
Wait, move u to the top and then solve that way? Oh, like the u, the square root of u on the bottom to the top.
Okay, you could have. Yes, that is one way. Remember, okay, I'm going to say this. There's so many ways you can solve this. There's not just one right way. Okay? There is one right answer, not one right way. Okay. So, is there a way we can separate this integral into two integrals? Yes. So this is the integral of u over the square root of u du minus the integral of 1 over the square root of u du. Minus because I'm left with a negative 1, and I just moved the negative to the outside. Okay, does this look a little easier?
Yes.
Okay, so now we're going to do what he said, and we're going to change the radical into an exponent. So this is u times u to the negative 1/2 du minus the integral of u to the negative 1/2 du. Okay, we got rid of all the radicals. Okay, u, if this is u to the first power, which is 2 over 2, and we add that to the exponent of negative 1/2, we have the integral of u to the 1/2 du minus the integral of u to the negative 1/2 du. Okay, from here it should be very simple to do the antiderivative because we isolated everything to make it easier on ourselves. Okay, so what would be the antiderivative of the first one? U to the 3/2 over 3 over 2 minus, what about the next one?
U to the 1/2 over 1/2.
1/2 plus c. Okay, we can simplify this. Instead of saying divide by those fractions, the same as multiplying by its reciprocal. So 2/3 u to the 3/2 minus 2u to the 1/2 plus c. That means our last step is to do what? Plug in what? U. And what was u? X plus 1. So 2/3 x plus 1 to the 3/2 minus 2x plus 1 to the 1/2 plus c. That is our answer.
Unless too big enough. Get the rest. No. I have a tiny pen for a reason.
Okay. Everyone with me so far?
Yes.
Okay, number 7 isn't bad. Okay, number 7 says that this is a tricky example because if we don't know our inverse trig, okay, we could confuse it and use u substitution instead. Okay. Okay, so for example, looking at this, let's say we did not know that this resembles an inverse trig. Okay, so we use the process of u substitution, and what would you have assigned u to be? 1 minus 4x squared. Okay, I'm going to tell you, you go through the whole u substitution process, you may or may not get an answer. Okay, it may put you in a repeating cycle of u substitution, w substitution, v substitution, y substitution, and you'll never get an answer. Okay. However, because you guys are all super smart, right? We know all our inverse trig. And this kind of resembles what inverse trig? Sine. Sine. Okay, right, because I'm going to write this here. What is it?
1/√1 minus x.
Okay, do you see how they're similar? Okay, so let's try to rewrite this to look like that inverse sine. So right now we're not doing any u substitution just yet. I'm going to rewrite this to be 1 over the square root of 1 minus 2x squared dx. Okay, did I change the problem at all, or did I just manipulate it? Okay, right, because 4x squared is the same as saying 2x in parentheses squared. I could give the square to both of them. Okay, when I do that, does it make it obvious what my u should be? 2x. So let u equal to x, which means du dx is equal to 2. So dx is equal to du over 2. So I have the integral of 1 over the square root of 1 minus u squared du over 2. I can move that divide by 2, which is a 1/2, to the outside, and I get 1/2 integral of 1 over square root of 1 minus u squared. And then from here, since I know about my inverse trig, I can say, well, I can take the antiderivative because I know that this is going to be equal to 1/2 inverse sine of u plus c. And then I just plug u back in, and I get 1/2 inverse sine of 2x plus c. So this one isn't bad if we had those inverse trig functions memorized. Okay, if we tried u substitution, if you want to try that on your own time, go back and do the whole process through u substitution. Let me know if you get an answer. Okay, so everything we just did was in indefinite integrals, which means we did not have any bounds. Okay, so on the next examples, we're going to evaluate the definite integral, so doing the same process of u substitution, but we're going to actually get an answer at the end. Okay? So looking at this one here. Okay. So for this one, we're doing the same process of defining our u. So what is u?
T3 plus T plus
Good, t cubed plus 1. So du dt is equal to what?
3t.
3t
squared.
squared, which means that,
dt is equal to du over 3t squared.
perfect, dt is equal to du over 3t squared. Okay, when I plug everything back in, I'm going to leave space for my bounds, and I'm not going to fill them in just yet. So I have the integral of t squared square root of u du over 3t squared. The t squareds cancel out, and that 3 is going to come out to be a 1/3. Okay, integral of the square root of u du. Okay, the reason why I did not fill in my bounds to be 0 and 2 is that 0 and 2 is represented by t. We need to create new bounds that are now represented by u. And we know that u is t cubed plus 1. So I'm going to plug in my old bounds. So 0 cubed plus 1. And then 2 cubed plus 1. Which means my new bounds are going to be from 1 to 9. This is the biggest mistake that you can make, is forgetting to change your bounds.
Wait, can you explain why we have to do that?
So the reason we have to do that is when we're using u substitution, we are changing the variable. Okay? For the integral from 0 to 2 is only in terms of t. But if we say that u is equal to t cubed plus 1, these bounds have to be in terms of u as well. So if u is t cubed plus 1, we just plug in the old bounds in for t, and we get the new bounds in terms of u. Which means if we had to do a double substitution, so we do a w substitution, would we have to change the bounds again? Yes. Okay, so then solving this, square root of u is still the same as u to the 1/2. So we have u to the 3/2 over 3/2 if we're doing the antiderivative. Okay, and I still have the 1/3 in the front plus c. Okay, and the bell's going to ring, but I'm still going to be teaching, okay? Stay if you can, leave if you can't. So we have this as the same thing as 1/3 times 2/3 u to the 3/2 plus c. Okay, bye guys. Have a great day. So this becomes 2/9 u to the 3/2. And then since we have bounds, we technically no longer have plus c, but instead this is solved at from 1 to 9. So this is equal to 2/9, okay? And then I'm going to plug in the upper bound 9 for u, okay? And then the lower bound 1 into u. So this is 9 to the 3/2 minus 1 to the 3/2, which is equal to 2/9 times 27 minus 1, which is equal to 2/9 times 26, which is 52/9. Okay? So notice when we did this one, since we changed the bounds, we did not have to go back and substitute what u was back in. Okay, we left it in terms of u, used our new bounds of u to solve for the answer. Okay, so I'm just going to go through the next one. So it's on the video. You don't have, if you need to go to class, right? Okay, so let u equal sine of x because that's the inside function. So du dx is going to be equal to cosine of x, which means that dx is equal to du cosine of x. So plugging everything back in, I have cosine of x times the square root of u, okay, du over the cosine of x. So cosine of x cancel, and I have the integral of the square root of u du, and I have to change my bounds since u is sine of x. So instead of it being from 0 to pi halves, this is now sine of 0 to sine of pi halves, okay, which becomes 0 to 1 by. Okay, so then I have u to the 3 halves over 3 halves, okay, solved at 0 to 1. So this is 2/3 u to the 3 halves solved at 0 to 1, which is 2/3 times 1 to the 3 halves minus 0 to the 3 halves, which is 2/3 times 1, which is 2/3.